Okay, we are now being recorded, and I'm going to switch up the audio. No, I'm going to leave it just like that. All right, so acids and bases. It is it after the things we've been through, it should remind you somewhat to some of the concepts we've been looking at, but there are certainly some new things, especially when we get into tomorrow's information. And I'm going to try really hard to make this applicable, usable in your practice as you head out into the medical profession, whether it's be dentistry or anything else. I actually ran into a dental hygienist who was switching up their career, not a PMI student, but to someone unrelated. So you just never know where life's going to take you and where the information you're learning that might seem pointless now actually comes up being something that is useful. Okay, so we will be looking at things such as naming of acids and bases. I don't worry about that too much. That's more of a memorization thing. There's not a huge, to me, I haven't found a huge rhyme or reason to naming acids and bases yet, but you see them enough times and you recognize the structures and the names that go with them. Okay. Uh, identify acid-base pairs and something called Bronsted-Lowry acid and bases. And before we even get to that, one of the bullet points that's not here, we're going to look at what are called Arrhenius bases really quickly. But usually when we're talking about bases in chemistry, we're talking about Bronsted-Lowry acids and bases and their conjugate pairs. Okay, you have a Bronsted-Lowry acid on one side of the chemical equation. You have the corresponding Bronsted-Lowry base on the other side of the equation, and vice versa. And you'll see what I mean once we take a closer look at that. Dissociation of strong and weak acids. We saw that a little bit in solutions, of course. Acid-base equilibrium. Across, especially in weak acids and bases. Look at Le Chatelier. Let's see, my French pronunciation leaves a lot to be desired, but we'll go Le Chatelier. Le Chatelier. Anyway, basically driving chemical equations in one direction or another based on their concentrations. Dissociations, pH, which can be somewhat confusing as a measure of the acidity and basicity of things that are in aqueous or water solutions. Okay, and how we can use those, and molarities. And we won't get to do a lab, so 10 and 11, not so much. Okay. So acids and bases, there we are. You don't get medical terminology, but here is a place where the Latin for acidus is sour, and they do tend to taste sour. It has some citric fruits here with citric acid, which accounts for the sour flavor in fruits. Okay. So let's look first of all at Arrhenius acids. Okay, real briefly. It's kind of the first way that folks used to look at acids. Okay. Is an Arrhenius acid produce hydrogen ions when they dissolve. So hydrochloric acid, of course, dissociates and produces protons, okay, and chloride. So that is considered an Arrhenius acid in this case. Okay. And they turn blue litmus paper red. Yeah, that's the way litmus paper reacts to excess protons to change the color spectrum from blue to red. Okay. Naming. This is probably as deep as I'm going to get into it, but if you see the ending ic, you have an acid of some sort, or either ic or OS acid. Okay, so chloric acid in this case, and chlorous acid. Okay, and that's just one less oxygen in those polyatomic entities from the chlorite and the chlorite. The acidic versions add your proton, you get chloric and chlorous acids. Okay, this is a whole chart of various acids and their names. You'll see the vast majority of them are ending in IC, hydrochloric, hydrobromic, sulfuric, all of these things, with occasional OS, phosphorus acid, sulfurous acid, and those other things. So that's about, you won't be expected to memorize anything like this. We'll certainly give you the names of these, any homework that you might see. And that is kind of a waste of brain space. So for instance, HBr is hydrobromic acid. Okay, tell you that. Number 2 is carbonic acid. Right there, carbonic acid. And the last one is hydrobromous acid. That's an example of the bromous acid version. Right there. Okay, circling back to Arrhenius bases. So we looked at Arrhenius acids, of course, producing the positive charges, the proton ion. So Arrhenius bases, on the other hand, are molecules that produce hydroxys, okay, with a negative charge on it. Okay, so the one I was talking about is sodium hydroxide dissociates in aqueous solution into sodium, and there we go. Not a proton to be found, but there is the hydroxy, right there. So Arrhenius acids, protons, Arrhenius bases producing our hydroxys. So typically with the bases, you just say what is usually a metal, sodium, potassium, barium, and aluminum in these cases, and follow with hydroxide, indicating there is a hydroxide that's going to be coming off in solution. And there we go, pertaining to dentistry, calcium hydroxide. I'm assuming that's used with some frequency in dentistry. And use that in root canals to get in there and fill up those root canals. Okay, and that's like, so calcium right there, calcium. Of course, calcium has a +2, so we need 2 hydroxides to counteract that. So you have the base calcium and then 2 hydroxide balancing the equations. If you're given a list of matching, you can kind of get the easy one. Sodium hydroxide takes C out. Calcium hydroxide that we just saw. Nitrous acid. There we go. The only one with a nitrous. Sulfuric acid, the only one with a sulfur in it. And then, of course, iodic acid, the one molecule that does have an iodine associated with it. Okay, you can use these little tricks to figure these things out until they become second nature and you just see them and know what they are. And trust me, you do enough chemistry, you just go, oh, there's sulfuric acid, there's iodic acid, all those things. Okay, so Arrhenius acids, protons, hydroxys. Bronsted-Lowry. are the ones that we use much more frequently. Brunstedt, I guess, must be Swedish. Okay, so that's an international subject. So, acids and bases. So, in this case, a Bronsted-Lowry acid is something that donates a proton. Okay, this looks familiar, right? And a base is something, this is where it changes, it accepts that proton. Okay, instead of the hydroxy, we're just looking at donators and acceptors of protons. Okay, and that, I don't find that a super great example. But let's look at this one here. We have ammonia, one of the main waste products of protein metabolism. Ammonia gives the urine its smell. Okay, so in this case we have NH3 and water in balance forms NH4. So you can see it has picked up a proton and a hydroxy. Okay, so in this case, we have conjugate acids and bases for each of our molecules here. So these are the conjugate pairs right here. So we can say that this is the Bronsted-Lowry base because it is accepting a proton. Okay, so the conjugate acid, and there's always a conjugate that goes in these, is the acid that would donate that proton. Okay, so the acid and base conjugate pairs in this equation for the ammonia is NH3 is the acceptor, NH4 is the donator, and of course we have the exact same idea going on with this conjugate pair up here. You can see that we have an acid, since it has donated a proton. Okay? And the base, conjugate base of water in this case, would be the proton acceptor. Okay, so you have two conjugate bases, two conjugate acids, and they go in lockstep, balancing our equations once again. Now, always talking about balance. That's a theme that we do see over and over again. Bronsted-Lowry, follow those protons, who's donating it and who's accepting it. So here we have Arrhenius acids and bases, Bronsted-Lowry acids and bases. Arrhenius donates a proton, it donates a hydroxy, and Bronsted-Lowry, all you need to do is follow the proton, the hydrogen charge, okay? So let's look at this a little more closely. Hydrogen, okay, and our aqueous solution, okay, dissociates completely, so it makes a strong acid, and we'll come back to that. Okay, we have picked up a proton here, and we have lost a proton over here. Okay, so we have a conjugate pair right there. We have a proton donor, a proton acceptor, right? Okay, donor is the acid, acceptor is the base. Okay, and likewise, we have water and hydronium. That H3O plus is called hydronium. The hydronium is the acid since it is donating a proton. Okay, and this is the base. Just regular H2O is the base since it would be accepting the proton. Okay, that makes sense? Sort of. Yes. Okay, well, let's work through some more examples here. So, but you do under the concept I'm trying to drive home of following the protons in each of the conjugate pairs. There, yeah, you could certainly be asked a question: what is the Bronsted-Lowry acid in this equation, or something along those lines? On the left side of the yeah, yeah, on the left side of the equation. Yeah, nor would I expect you. That's yeah. What would you need me for if you could already do this, right? Okay, so let's run through another example. We have hydrogen fluoride. Okay, on one side of the equation, again in good old water, weak acid because it goes in balance, so we have arrows going both ways. There is our friend, the hydronium ion. Once again, you will see hydronium ions all over our study of acids and bases. Okay, and then fluoride. Okay, so we know we have one conjugate pair right here, hydrogen fluoride and fluoride. So this has donated its proton. So it is the Bronsted-Lowry acid. This is the Bronsted-Lowry base, okay, because it is a proton acceptor, proton donor. And then up here we have our hydronium and regular water. We have the proton donor, which is the acid, and water, which would be the proton acceptor in this case, and that's the Bronsted-Lowry base in this system. Okay. And notice, I mean, those of you who kind of like looking at things visually, you have an acid and a base on one side of the equation. You have an acid and a base on the other side of the equation. And then to tie it all together, you have the conjugate bases of those molecules and the conjugate acids and bases for the, let's see if I can get that to highlight, the conjugate acids and bases for the other. So acids and bases on one side and their conjugate acids and bases on the other side. So you won't ever get two acids on one side and two acids on the other side. So if you come up with that, yeah, you did something wrong if you're looking at Bronsted-Lowry's. Okay, acid, base, yes. So something like this might be in each of the following equations, identify the Bronsted-Lowry acid and base. And then on the left side, so as we identified HNO3, we got our acid. Oop, move that down. Our acid right here and our base right here. And then we also had our Bronsted-Lowry acid here, our Bronsted-Lowry base over here. And then we also took the extra step and identified their conjugate acids and bases as well. So sour, yeah, acid, arenas. Base would make a hydroxy, chalky tasting are bases. Washing your mouth out with soap, I guess. An electrolyte, both of them form electrolytes, like we saw when we were looking at solutions, and produces protons. Of course, that is an acid. Okay. And then the last thing I'm going to kind of look at here is the relative strengths of acids and bases. And we saw this weak acids, yeah, and when we were looking at solutions. So a specific form of this is when we're looking at acids. So weak acids weakly dissociate in water. They don't completely dissociate. So hydrofluoric acid is the only halogen, which is a weak acid. That's just a fancy say of everything that is higher up on the periodic table that's a halogen will form a strong acid. That's all that's saying. Okay. But our stereotypical, we always talk about hydrochloric acid, stuff that's in our stomach. For instance, hydrochloric acid in water will dissociate, and you have an arrow going in one direction indicating complete dissociation into our hydronium ion right there and our chloride. So complete dissociation in aqueous solution. Okay, and then hopefully just kind of in your mind's eye, figure out which one of those are the acids and bases right here. And I'll just say it really quickly, just see if you got it right. That's the base, and that is the acid. Okay. Then we have the conjugate acid and base on the other side. Okay, so that's a strong acid. Weak acids, just like it sounds, do not completely dissociate. So we have something like that in aqueous solution. We indicate those by saying there is an equilibrium on both sides. It doesn't push all the way to the right-hand side. There's an equilibrium that ends up with, again, our hydronium ion and carbonate with its negative right there. So a weak acid, incomplete dissociation. Of course, we have the acid here, the base here. Okay. The Bronsted-Lowry acid and the Bronsted-Lowry base. And this is an example of a weak one, that a weak acid that does not completely dissociate. Okay, hydrochloric acid, just exactly that. This is a graphic representation, I guess, a visual representation. Hydrochloric, it dissociates completely into hydronium and chloride. Hydrogen iodide would do the same thing. And these are some bases that go from weak up to strong, just meaning that they will dissociate more completely, I guess. Higher levels, the higher up in the table that you go. Okay. And then weak acids, we looked at hydrogen fluoride when we looked at the relative strength. I think we started off with hydrogen fluoride. Yep. Hydrogen fluoride right here. You can see these are in equilibrium right here. There is just slightly more of the hydronium ion formed, okay, right here, and most of it has stayed as hydrogen fluoride. The bonds are strong enough to resist being torn apart by the polarity in the solvent, water in this case. Okay, but there is some hydronium ion being formed here. So if you add the orange piece and the green piece on top of the purple piece, it will equal the purple piece on the left side of that equation, chemical equation. Okay. Once again, strong acids at the top, weaker acids as you go down the slide. So in hydrochloric acid, it completely dissociates into hydrogen and chloride. Okay. And weak acid will have incomplete dissociation. And I did indicate that with this example right over here. In fact, that's not quite the same one, but another form of a weak acid. Okay, and strong bases, just like you can hopefully see kind of where I'm heading with this. Strong bases are bases that dissolve completely or dissociate completely in water. I see a lot of metals combined with hydroxides, lithium hydroxide, sodium hydroxide, potassium hydroxide, all strong bases. Okay, so they would dissociate completely. Right? Potassium hydroxide dissociates completely, just to have the arrow leading us to potassium and hydroxide right there. Okay. Let's see. Yeah, so let's just run through this table here. All these is just taking a look, hydrogen bromide, hydrogen nitride, those will dissociate completely, but all they're asking you to do is refer back up to this chart and to answer your question. You're thinking, am I going to have to memorize which is strong? And no, you should be familiar with the nomenclature, whether this is a single arrow or a double arrow going both ways, and what that indicates in relations to weak acids and bases and strong acids and bases. So you can just look at each of those up on the chart and place them as strong or weak acids and bases. Okay, and you can do the same thing on this table right here. Simply looking at the table. No, you will not have to know that information off the top of your head. And this, I am going to stop right here because now we're getting into the idea behind pH, is the dissociation of water. The pH, when you say something's acidic, something's basic, our normal blood pH is 7.4, yada, yada. All these things we see normally. Stomach acid content is pH of 2 to 3. For instance, in humans, we're talking about basing that on the dissociation of water. And that is where I want to pick up tomorrow on that subject. It's a whole new can of worms for us to look at. All right. Okay,